So my name is Cecilia. I'm from Taiko Labs. So Taiko is a base rollup, a layer 2, and we're working on a composability solution, synchronous composability solution for like L1 and L2 or L2 and L2 interoperability called Gwyneth. And the topic of my presentation is L1 and L2 interop and programmable block. And it's specifically regarding our design with something called ultra transaction that we do share settlement of validity rolled up. Yeah, so I did a presentation before because this is like tailored to some other event that I did this presentation about composability. So this is like, so I said previously on composability, but like just for the context, if we want to compose, I'm not sure about like what are people's knowledge on like L2 blocks, settlements, and composability. But like if we want to establish share settlement together, the blocks need to be built with a share sequencer and to facilitate cross-chain call. And L2 to L2 interoperability can be achieved if there is state locks on both chain. So in this diagram over here, if we build two L2 chains in a share sequencer, there need to be certain protocol that like obtain the state lock of L2 of both L2A and L2B, which means we can do that either with pre-confirmation or with execution ticket. And if we obtain the state lock for that and we build a block together, L2A and B can easily interop while we settle the block to L1. And for the current development in like the Ethereum sequencing ecosystem, we have inclusion pre-confirmation, which allows rollup to settle block together somewhere in L1. And in that case, like our goal is to do like composability with L1. But in that case, L1 state is not locked, and the builder cannot make any assumption about the L1 state. However, with execution pre-confirmation, so how many people know about pre-confirmation in this room? No? Okay, so like pre-confirmation is basically how like Ethereum L1 validator can pre-confirm transaction prior to this 12-second block time. So your transaction usually gets settled whenever a L1 block is out, right? And all of the block need to go to the PBS pipeline that like is built by the builder and then confirmed by the sign up by the validator and finally make it to L1, right? So a new solution proposed by Justin Drake and the community is that like we have proposer making commitment in advance, right? The proposer commit to a pre-confirmation provider or a pre-confirmation gateway that this batch of transaction is going to come in, and we're going to include it in some future point of time, right? And it's usually currently it's usually done by like secure by staking. So we basically have an AVS for a certain subset of L1 proposer opt-in. And these proposals will be like, okay, I work with this gateway who specifically sequenced for this L2 or this application that does like, for example, application specific sequencing. And I'm going to give like settlement commitment for these specific set of application. And this is called proposer commitment. And now like some of them are live, some of these protocols are live on mainnet, but like a large number of them are still like under development. So yeah, so that's like the context, right? And there are two types of pre-confirmation over here. So the one that I was just talking about was inclusion pre-confirmation, basically promising people that we're going to include your transaction later on. A more sophisticated type, a more difficult type of that is called execution pre-confirmation. Basically, I tell the user, for example, I'm going to execute your swap with a certain amount of slippage. Or like, I confirm on, like, I pre-confirm the outcome of your execution. That's like execution pre-confirmation. And that is very difficult to do because if you confirm like the result of certain swap, right? Basically, someone else is gonna come in and fuck you over. You know what I mean? Like I confirmed, I thought that ETH price is gonna be 27, like 3K, and turns out being 2K, right? and like that will basically like option pricing that you just kind of lost your money. Yeah, so these are those two type of pre-confirmation, and we as rollup, we use that for settlement now. Yeah, so for these two types, for if we have execution pre-confirmation for as a L2, we can basically read and write L1 as we want, because we basically get pre-confirmation result of L1 execution, which means if there is like a L2, for example, a flash loan that you borrow money from L1 back to L2, borrow money from L1, bridge into L2, and pay it back to L1 within one block, we can do this, right? We can do like interoperability freely on L2.
So it's a requirement. You need pre-confirmation support in order to do cross-chain synchronous transactions.
Well, I'm gonna go over that later, right? Okay. So like the specific requirement for that, like, but then the available pre-confirmation are these two types, and then there's another thing called like top of block pre-confirmation, which means that the validator not only promise that like we include your transaction, but also put that at the top of the block. So that means we can basically observe the L1 state from the previous block and build up L2 interoperable transaction on top of that, right? But in that case, we can like read the L1 state as we want, but we only have one chance to write it back. Yeah, but I wouldn't say it's a requirement though, because like usually how L2 settle is like we don't go through pre-confirmation nowadays, right? Like you just like propose the block. However, this is specifically with like base rollup. If base rollup wants fast finality, then you need pre-confirmation from L1 validator directly, because in the base rollup scenario, you don't have a centralized sequencer, meaning you don't have like a centralized sequencer telling your L2 user that your transaction is included within like 250 milliseconds. Your block time basically is like at least 12 seconds because you're base, right? You propose with L1. But if you have like validator pre-confirming this in the L1 PBS pipeline, then you can tell your base rollup user that we have fast finality, even with decentralized sequencing, right? So this is how we solve this question with base rollup. Yeah, so I guess like for Taiko, we already have, we're gonna use this to speed up our block time, which is currently about like above 12 seconds, right? And then we want composability with like L1 and L2, right? So the goal is to do L1 and L2 composability back and forth. For example, doing the L2 flash loan with just top of the block pre-confirmation. And the design that we come up with is called ultra transaction, which means we basically want to do shared settlement of multiple L2 rollup instance in one fat transaction that we propose to L1. And which this fat transaction will not only update each rollup state, but also execute all of the cross-chain calls in one path. And the intuition behind that is when a single transaction is executed, the EVM is instantiated once, which means there's no unknown L1 transaction that jumps a queue, right? And upon the state lock, you have like, you seize control of all of the states, right? You can observe the previous L1 state, and since you have the state lock promises of different L2 instances, you also have like the control of different L2 state throughout the lifespan of ultra transaction. And a bonus for that is we can also use EVM's transient storage, which is like a new feature that EVM provide that, so in normal storage and smart contract, it's like it's there forever, right? You gotta pay for that. But for transient store, it's much cheaper, and then it got swipe up after the transaction is finished. So you can like utilize that for kind of like data passing across L2 while these little L2 transactions are calling each other. And by default, we have atomicity because since this is one transaction, if it revert, it just revert altogether, right? So it's automatic. You don't have the concerns over if one L2 settle, the other doesn't settle. then basically the user are fucked. Like you locked money on one chain, and you're supposed to mint on the other, but the other L2 is not settled somehow. That is like one downside. That is basically the main problem where people working on the space are trying to solve, right? And we solve it by just forcing them settle together. And we basically also bring the settlement dependency and cross-chain constraint within the EVM, into the EVM, and enforce them as like EVM logics. So there's no need for like external protocol to enforce, if this settle or that settle, like we have to revert. We don't have to deal with any of that scenario. And we basically bring programmability into cross-chains block space. And the validity of the whole transaction is being enforced by proving the building process of this Ultra transaction. Yeah, so the question is, how do we actually build this fast transaction, right? If you guys are familiar with account abstraction, this should immediately rings the bell that like, because like AA, account abstraction allows a bundler to batch each user operation and execute it all together on chain. And then that like immediately should remind you of like, that's how rolled up kind of like batch out of the L2 transaction and rolled it up on chain, right? A rolled up proposal is basically a account abstractions transaction that you like settle out of the user operations. And how account abstraction work is that like the user Alice will have a smart contract code at her address, and the front end will build user operation as she interact with the wallet, right? And the bundler on the back end will batch out of her user ops and call this function execute. So as the bundler calls the thing, the transaction origin will be the bundler, and this EIP 7702 will allow the subcalls that coming out from the smart wallet having this message.center equals Alice herself, right? You can set the code for your EOA contract so that it has this code permanently, and anyone can cause it on your behalf. And this is we're also inspired by this to like in our design of like cross-chain application. So we let cross-chain apps to either inherit this interface or we deploy a proxy of this, and so that proposer can batch cross-chain messages. And we also enforce all of the cross-chain application to have the same address, so that proposer can relay call of, for example, like a Uniswap L2 instance into the mirror instance of Uniswap on L1, and calling Uniswap to interact with the L1 instance on Uniswap's behalf. And in that case, like the transaction.origin is the proposer, and we require that like it's indeed being updated by the proposer, by the permissioned proposer, or like the permissioned smart contract, which is like our protocol contract itself, and the message coming out of that will be equals to Uniswap, right? So you basically, through these interface kind of implementation, you kind of enforce that any calls that are initiated by L2 through the L2 RPC kind of is being relayed to L1 by the block building process. And that transaction can go out and interact with its own instance on L1, or the other instances of other contracts, for example, USDC, right? Yeah, and all of the call being relayed up to L1 will be executed in the L1 runtime. So for example, if you don't have money in L2, Uniswap, you can basically initiate a call to L1 and using L1 liquidity, right? So that's the intuition behind this. And so like, as we build up the Ultra transaction, right? Like our builder will like sequence transaction in our L2 node, and we eventually collect out of the L2 to L1 call, like I just said before, and kind of just put it in a big array of like subcall of like account abstraction based subtransaction that we call the L1 instances. So. And I find it personally very important to differentiate this notion of L2 runtime and L1 build time, because A shared sequencer will have access to both DB locked at time t when it's building the thing. And Gwyneth will allow like a builder to swap DB at build time. So this is how like a block has been built in L2, right? Our node implementation will have the view of both L1 and L2 DB. And when we have like a transaction from L2 calling into L1, we like swap out the execution environment, swap out the DB instances in the execution, in the EVM execution environment, and then we just execute the L2 transaction and the L1 transaction locally in our node, right? And then as we propose, we'll settle the result of the execution, which is like L2's state at t+1 directly onto L1. But then this part that should be executed on L1, which was the relay transaction to L1 that is supposed to be executed at L1 runtime, need to be relayed across. So when we hit L1, the L1 node will see a call, right? That are being like instantiated over here, that are being instantiated over here, and then it will like iterate through the call and eventually execute the call on L1, right? So after the L1 EVM is run to settle your rollup, like it settle your rollup by recording the latest state of L2, well at the same time, it iterate through all of the potential L1 calls and execute those one by one, and eventually progresses the L1 state. So towards the end of this section of ultra transaction, you kind of have like L2 t+1 and L1 t+1 all together. So this is for L2 to L1 transaction. Yeah, and some nuances is that like the L1 runtime only has access to L1 DB, right? If a node is witnessing a L2 proposal to L1, like an L1 node, right? It doesn't care about the L2 instances. It doesn't care about the L2 chain. It only sees like these stuffs, right? So the nuances between these differentiation is that like, okay, we built L2 that has access to all of the available data, but for the stuff that L1 need to run, we kind of need to like separate them out and put it separately to the L1 runtime so that the L1 can process them. And L1 runtime needs like a Oracle access to all of the L2 output to complete a L1 to L2 call. And that brings me to like the how we do L1 to L2 call, right? Because I just went over how L1 process like L2 to L1 call, right? But if a call is instantiated from L1, right, within this builder instances, we have a call calling from L1 and from L1 Uniswap to L2 Uniswap, then this call itself will be executed as a call in the L1 node when we sync it up there. And when the call hits the spot where it needs L2 access, right? But then we're at the L1 runtime. We don't actually have the L2 state to build it up. So we kind of like insert the execution outcome of that L1 to L2 call into a oracle, into a L1 oracle. So this towards the end of this execution, this call will basically retrieve the output from the oracle and complete this L1 to L2 call within the L1 runtime. Yeah, so that's how we do like both from up and down from down to up. And the oracle basically acts as a lookup table for pre-processed information that L1 don't have access to. Yeah, so this is what we have so far, right? L1 to L2, L2 to L1, and L1 to L2. We collect everything and put it in a big oracle for like oracle updates. And what about, and there's another thing that we implemented, which is like state diff. This is another way for us to do cross-chain calls. So instead of like relaying call to the runtime, we kind of just directly update them. We kind of just process the result at build time and apply the results of the execution. So imagine we have like two L2 instances that are being built in this super builder, right? And in fact, L1 doesn't care what are happening between these two L2, right? Because in this case, there's no message passing between L2 to L1. So what we do is we kind of just collect the state diff caused by these L2 calling each other, directly apply to the local DB, and just propose the state delta to L1 for data availability. So as you settle the rollup transaction, you will have like these things in the blob, which are both L2's transaction list and the state diffs that are being incurred by each other, right? And there's also a scenario where we kind of directly want to apply state diff to L1. So instead of like relaying the call to the L1 instance of some mirror contract of cross-chain call, we just say that, okay, this is the diffs that it costs. And we just call this, the proposer will call this function as an upstate, as a proposed block, and say that these are the slots that are changed. And we directly apply the state diff. And in this way, like L1, so all of the chains that are settled together, L1A and L2A and B, and also L1 itself, all progresses to the next state. Yeah, so the state diffs computation is over here. Like we like extract out of the diffs and just apply it. And another side note is that all these operations can be built with like random order, like the order at which the builder wants, right? Whichever way that extracts the most cross-chain MEV can be applied to the building process. So it's not necessary to settle this call first and this call and following by this call, right? Like you can like build it interchangeably as long as you extract the maximum amount of MEV. Yeah, so that brings me to this topic of programmable block. So we think that like L1 and L2 interoperability and like cross-chain interoperability are programmable. And this is like the whole runtime view. This is a runtime view of an L2 block proposal, right? You first have a Oracle setup and then incoming transaction into the L1 runtime and the state diffs application, and also followed by the L2 settlement. And a good thing is this space where you have like the incoming subcall into L1 runtime can also be used as a space for regular account abstraction operation. So let's say there is a L1 transaction fetched from L2 RPC directly going into the L1 contract. We can just literally build it as a account abstractions user ops. And in this way, like the builder gets to sequence more transactions as it wants. So like a L2 super builder is also an instance of just a regular builder, right? And in the future, if everything is going to be account abstracted, then account abstraction itself is going to settle on L1 block as a big transaction anyways. So like I would say this is like account abstraction is a subset of this, of like a settlement, a big settlement transactions. Yeah, and also this extension oracle, so the oracle at which L1 can access pre-processed information from L2 that are being proven by validity proof of L2, can also serve as a syscall that set up the extension oracle for the rest of like any proposal transaction, that any settlement transaction for any apps, right? You can have like, for example, a Hyperliquid, like a trading application that are app specifically sequenced, and these oracles are the oracle access with the price, right? And as you rolled up or as you settle a bunch of user operations from the trading apps, this extension oracle can serve as an oracle of like the outside information that whatever this application needs, right? And yeah, so like the realization that we have is Ultra transaction is a rolled up proposal as much as a AA settlement. And the Ultra transaction implements execution pre-confirmation of L1 transaction, which are these, right? These are basically execution pre-confirmation of a bunch of L1 user ops as well as L2 transaction themselves. A cross-chain builder is a shared sequencer, and it is also a pre-confirmation gateway that offers you pre-confirmation for anyone that are that wants to interact with L1 or L2, right? And it works with all base rollup on a sequencing protocol that obtains the state lock. So as long as state lock is secure, then we can run this protocol for all base rollup. Yeah, and for validity, there's also like some nuances that we can like. There's also some implementation choices that we can pick to like how to prove the validity of this, right? You can like prove the build time, meaning like you basically put the builder into a TAE or a ZK VM, and the output of that is like you prove how your builder generates a proposal, right? Or you can choose to prove the runtime, meaning you kind of like prove regarding each chain's view, right? If you're a chain A, that you only care about chain A's settlements and chain A's transaction, you can run chain A's EVN in its own environment and prove the validity of chain A's, or you can run the validity proof of chain B and build a aggregation proof later on, and you kind of like constrain like the state diffs and the input-output pairs with a lookup table that requires custom logic and like the ZK program that you write. Yeah, and we basically, and in that way, we basically aggregate the proof of like the L2 settlement with the L1 settlement towards the end. Yeah, so here are some use case of what we can build, right? Like I just said, like for example, Hyperliquid is like one example. As we know that Hyperliquid is its own chain that is also a perp stacks that has like order books for longs and short, and a clearinghouse that like calculates users' margin to do liquidations, and also a very important oracles for price. So in the current Hyperliquid construct, the validator will have to publish like price every 3 seconds, and like their chain is basically customized for consensus on sequencing the orders and securing like the oracle price updates, and also like clearing everything to do liquidations, right? So we can use a extension oracle as this like oracle as a oracle entry point to like where Hyperliquid update its price, and basically you can migrate Hyperliquid as a layer 2 app chain that uses L2 mempool to sequence the user's order, the longs and shorts, and apparently you can use like L1 smart contract as a settlement contract as much as the clearinghouse that compute like the rates and all of the prices, right? And a nice thing that you have from like as a Ethereum L1 is that if you have all these Oracle contracts on L1, you also get composability with Chainlink or Uniswap. Like for example, this Oracle not only can be updated by the L2 sequencer, it can also like query from the other price sources, and which like gives you much precise pricing for the price computation. And also like due to our design for like L1 and L2 interoperability, you can basically do like deposit and withdrawal within one block, right? So like everything would be instant. So like the goal is to let Ethereum enable Ethereum to have fast confirmation layer 2 like Hyperliquid using the base infrastructure as it is, right? You don't need any extra things. With every infrastructure ready, you can basically migrate Hyperliquid on Ethereum. And also another use case is, for example, for Unichain. So like, do we think that Unichain really solve fragmentation of liquidity? Like Unichain is trying to convince people to like migrate their money to Unichain as a uniform liquidity layer. However, we think that like may as well just put all the money on L1 and just like I said, like you can like with a synchronous composing application, you don't need any liquidity L2 to execute the stuff that you want, right? So assuming Uniswap inherit the interface that I just talked about with like L2 mirroring instances, like you can literally have empty liquidity, and the builder can process L2 initiated swap on L1, which like gets the benefits of app specific sequencing, right? If this like Uniswap L2 process swap on L1 and sequence on L2, right? Like that directly access to L1 liquidity. These user operation can basically be sequenced with MUV considerations. And you get the benefit of app-specific sequencing where this Uniswap L2 is specifically sequenced to update the liquidity status of Uniswap L1. And L2 user can also directly use flash flow, meaning like you borrow money, you pull money off directly from L1 and use it to do whatever on L2 and bridge it back to L1. In that case, this empty instance of Uniswap on L2 just serve as a liquidity entry point, right? You don't need anything to because a lot of like L2 developers, the difficulties is they have to like spend a lot of DB effort to like convince all these liquidity providers to onboard their L2, right? With like something like this, you basically need to like get to save a lot of time and money from doing that. Yeah. So a lot of people are bearish on share sequencing because people think that like no big rollup is gonna give up on sequencing rights to let some external party to sequence for them. But I'm actually like pretty bullish with the progression of like base pre-confirmation infrastructure because we think that like the adoption of share sequencer only comes with base pre-confirmation, where L1 validator give pre-confirmation or give proposer commitment to all these different gateway. So how it works is that, for example, in the future, like wallet can directly work with L1 validator, where the wallet submit user bundle as like account abstraction bundles, and the L1 validator would directly give confirmation to the wallet front end. So like you can have like a very flexible pricing model, for example, like a subscription model for a wallet for gas sponsorship. And in the L2 use case, you can also give like pre-confirmation to these builders that are sitting behind a pre-confirmation gateway. So these gateway will give like confirmation to L2 transaction, which in the backend it connects to a certain set of L1 validator that confirms these transactions, right? And it makes sense for this architecture to have like all these instances of base rolled up interop behind the gateway, right? If we have multiple L2 instances, and we can literally put one builder for them, and like and synchronous solution like Gwyneth will be like sitting here to sequence for both chain. And we can also have like inter-cluster communication to roll up that work with, for example, OP stack, right? Like this arrow here basically represents some like inter-cluster protocol that secures state lock for these like yellow chain and this green chain, and everything can settle together with proposer commitment. Yeah, and I think, right. Yeah, so that was basically what I was talking about. And I think shared sequencing standard can also like sit in behind the gateway. And all of that comes with the premise of base pre-confirmation. And if people are familiar with like what Justin Drake has proposed and the current progression of Fabric, which is like a coalition that try to accelerate all of the base rollup ecosystem. So this is like literally, and this is like one slide posted by Justin Drake, and like most of these infrastructure are being delivered under the way, and it has everything that we need to do synchronous composability on base rollups. Yeah, and I think the future is very bright, and we should like continue on this path so that we can unify Ethereum in the very end. That concludes my presentation. Thank you. Any question?
I
Yeah.
have like 5 questions. So, Gwyneth,
Uh-huh.
that is its own RPC, or is that an own network, or is that like an updated version of Go Ethereum?
Oh, in terms of implementation, we use Reth. We basically modify Reth,
Yeah.
and we change its database, right? Like we modify Reth such that it can sequence with multiple database, and we also modify like EVM inside Reth so that it can do something like this, right?
Okay. Yeah. So it's still the same Ethereum RPC,
Yeah,
Ethereum RPC.
yeah.
So if I'm gonna do my cross-chain arm
Uh-huh,
transaction,
uh-huh,
and today
uh-huh.
without this, I make a transaction in chain A, chain B, and if the first fails, my second one's still gonna run. But how does that look like here? Like I make a call to specifically this modified Reth that is part of the Ethereum RPC, and like if it fails on supported preconf chain A, then it will also entirely fail.
Oh, I guess like the whole point of what I talked about on like cross-chain block building is like your transaction gets settled together, right? So here, right? Like if this is your transaction, right? It started on chain A and it wants to go to chain B, right? It will be built by the builder locally, and it will settle together as we propose for both rolled up. So like the premise is that like we have to have the sequencing right for both A and B, right? What you're talking about with like you do something on A and B, A can be arbitrum, B can be optimism, right? You have to go to two places to do two separate transactions, and that's not considered synchronous, right? You're basically doing a bridge and then a bridge, and hopefully they both settle, and you're basically manually doing everything, right? And what we're trying to do is we allow smart contract developer to develop smart contract that allows you to like go across chain, and our sequencer sequence in regard of those like the execution of those smart contract that goes through different DB that settles locally and propose them together, right? So it's a programmer's interface as much as a super builder, a shared sequencing solution.
The atomicity is the same as a normal L1 Ethereum transaction. So if something reverts on the other chain,
Yeah.
then either you can make your whole transaction revert, or you can catch the revert and do something else.
So I'm assuming for Gwyneth, you guys deployed some contracts to Ethereum, and I deploy my contract to Ethereum layer 1, and in the contracts that you guys deployed, it shows your supported L2s. Like there's like some, and like if I want to make my cross-chain call, then in my contract, I will specify, or I'll import your contract and say, okay, like I perform some check, like it's either one of these chains that's supported when I pass my call towards the params in there.
Okay, I actually have like a demo.
So this is like a generalization, which is not completely, because you try to like generalize to like, okay, how do you do like optimism by arbitrum?
Yes.
So for Gwyneth, for now, it's just like one contract, which can contain an infinite amount of L2s. And so, like if you try to like get arbitrum and like optimism in it, then there's like you open like a whole can of worms.
Yeah.
Because well, what about like the settlement? Like what about like reorgs? What about like all these kind of things? So currently, that's not yet completely like thought about. So for now, this is just like all Gwyneth L2s, and because they're like uniform, it's like very easy to enforce these things.
I see.
Right. So if you're thinking about like smart contract experience, right? This is like how transfer function looks like on Gwyneth, right? X transfer from chain to chain, and this transaction is basically like a chain A containing chain V, right? Because you're going from chain to chain, right? And in this case, like our DB will have to have like access to chain, the from chain and the to chain, right? And they will like by default settle together.
Yeah.
Right. Yeah, and then
So like Gwyneth is a different binary than the standard out-of-the-box Go Ethereum?
No, it's different.
Yeah, it's a different binary. Okay,
Mm-hmm.
So
I understand this now.
basically, the only change we do is add like this extra precompile,
Yeah.
which allows you to switch chain
Mhm.
inside Solid. Oh, well, yeah.
Interesting.
Yeah.
But for now, only the base rollups are supported, so not like
Base roll and also rollups with real-time proof.
Right.
Yes, real-time proving, because you can't wait 7 days until my
For
transaction.
for L1 synchronous compatibility, you need to have
Yes.
for to support all users.
Exactly. So that's the requirement. Yeah, I was curious about the requirements.
So you cannot even bring arbitrum optimism in it because simply you cannot prove the thing when you need to prove it.
Exactly. So I'm stuck doing a shitty async cross-chain arb there. Okay.
Yeah.
So So if I want to launch a DEX in a new L2 that's not based,
Mhm.
and I want to source L1 liquidity, I'm also going to have to force people to bridge over.
Yeah,
Still,
because you need to. Well,
Okay.
yeah,
or
real-time
like
proving-
hope, not even force. Just I sit there and I pray. And okay.
Mhm.
Makes sense.
Just the thing
But-
we're trying to sell, as in like it is.
But how are based rollups then cheap? Like I get it with
why would they not be cheap?
so my knowledge is on traditional OP, like it's a different network, but I understand like based rollups that's within Ethereum, right? That's
Mhm.
that's updated. That's a different binary that from the execution client that's running on the node. Okay.
Mhm.
And how's that cheaper then? How's executing a transaction on there cheaper?
Well, because like you batch propose the transaction, so like the
You still do that, yeah.
yeah, I mean like it's the same as all the other L2, right? Like
Yeah.
it's essentially its own chain, right? We're running a forked geth,
Yeah.
and like the geth is its own like base like L2 chain,
Oh, but
right?
then you have a
But-
different RPC URL.
Yeah, of
Than-
course.
than Ethereum.
Yeah.
Oh, I see. I think I understand this.
But yeah, I mean the cheapness comes with, especially with like base rolls. Okay, you well if you want L1 synchronous composability, you only have like one L1 slot to do batching, right?
Yeah.
So, but the benefit of base rolls, of course, is like, hey, you can actually settle 100 L2s together in this one L1 block, and so you have like aggregation in a shorter amount of time, but like a larger like volume of 100 base rollups. Well, you put them all in like single block space
Yeah.
and compress it together.
Yeah.
So you get
And each rollup is its own chain, so you can basically adjust the base fee and transaction 1559 on L2, right? And you batch propose like the fixed cost for us as a rollup operator is to roll it up, right? Like to propose a transaction, we have to pay L1 DA and L1 execution. But for the user, like your transaction L2, right? It's cheap.
I understand.
Yeah.
Finally. Thank you. Other people have tried and failed.
You succeeded. Congratulations.
Yeah, and those guys were doing interop.